say you have a box with mass of 20 kilograms staying on the surface, when this surface has some roughness, so the coefficient of the static friction is 0.3, right? And somebody applies the force 80 Newton at the angle of 30 degrees. So what the thing that we want to do is to say that what happens next. What happens next? So I have some possibilities. The first thing is just nothing's going to happen. It's going to stay at rest, right? That's one option. The second option is this thing is going to start moving, right? Sliding. And the third one is this thing to tip over, right? So if this force, let's say you have something very tall box and you have a force P like 1 kilonewton, right? So you can easily see that this is going to tip over, start like rolling depending on how much force you put it on it. So that's also one of the cases. So we want to consider what happens next if I do 80 Newton at 30 degrees. So what should we do? Okay, every time I want to solve the problem, I have to show my 5 steps. Choose the system, draw FTD, draw it region, solve them, and then verify the results. So those are all the steps I need to take. So the choice of system is so easy here. Why? Because we only have one part, right? So I say, okay, this is the borderline, and this is my system. So I draw it here. That's the system. Now, start pick a point, like always, to get the surface force, and walk around it to get all the surface force. And as you can see, we explained in the last class, the friction force is a distributed load, right? So, and also it's not uniform. So if it was uniform, you would put it as center. The area center is center. It's somewhere, somehow, it's like you have more friction here than the other end, right? Let's say, you can see it right here. Let's say you put a force here, P, 10K, right? You have more pressure here than this end, right? Therefore, you have more engagement between the surface roughness, then you have more friction here than this end. So what I'm trying to say, this friction force has a geometric center that we don't know because this is such a complicated force. But we know that the total reaction is a friction force this way. Why this way?
Because that's the
opposite direction of possible movement, right? And also there's going to be a total normal force this way. But we don't know at what location it acts because we don't know the geometric center of this, the area center of that, right? So this could be also the other way. This could be the other way. So at one point, at one side, the geometric center is shifted one side, we don't know. So let's say just pick a center, this is the center, with respect to center, right? And let's put this at the location with the unknown distance x to the center. So I put the total resistant friction force and the total sum of normal forces. So that two unknown component, I put an unknown distance x. So how many unknown are introduced by just this friction surface? 3. A location that I don't know, a friction force that I don't know, and a normal force that I don't know. All right, excuse me. Then you continue walking on this dash line. The next thing you caught It's 80 Newton. There you go. 80, the angle is given. 30 degrees. And also, the vertical distance is given. So I put it. For the friction, because I don't have the geometric center, I'll just put X because I really don't have it. I don't know where it acts on. Continue walking, and then you come back to your start point, and you're done with the surface force. Now, what about body force? Do I have a body force here?
Yes.
Yeah. The body force is 20 times 981. And assuming that this box is uniform, so it's going to act at the very center of it, the geometry center, right? So that's my FTD. Don't forget to check my, I showed my system, FTD. Now write my equations. Summation of portion. X0, Y0. Let's say your XY is in this direction. Usually the default is this way. But look, we can rotate it. We can move it. We can put it here. We can put it. It's your choice, right? So I use this system. So the direction of the summation of force in X, let's start with this. What should I put?
Negative F.
Negative F. 0. 0, it doesn't have any X component, right? Plus 80 cosine 30 is equal to 0. That's the first equation. The second equation.
And
N negative 20 times 981 negative 80 sine 30 is equal to 0. And the moment equation. Now I give you some candidates. Let's say this is point A, point B, point C. Which one is more suitable for writing moment equation? C. You see, these are known. This is known. There is no point to get a reference point that all known forces are acting on. We take a reference point that most of unknown forces are going through. Right? Just I put a stop C here. Summation of 1 with respect to point C is equal to 0. So I get, let's start with this. What should I do with this? Move it. Down, right. So 20 times 981
Times X.
times X, positive 180. Positive, that's right. This one, let's consider the X and Y component. The X component is 80, put it here, 80 times
0.2.
cosine 30, right? And then move it. Where should I move it? Right here. So the moment is from here, the moment arm is from here to here, which is equal to
0.2.
0.2, positive or negative?
Negative.
Negative. Then the vertical component, which is 80 times
Sine 30.
sine 30. All right? So, where should I move it? Up or down?
Down.
Down. So the moment arm is from here, you see that? From here to here. And what's the distance from here to here?
What's that?
Yeah. Times X plus 24. What else? That's all. Right? Is it equal to 0. So these are my equations. This is the first equation. right? So let's first solve for this one, right, x. In fact, I'm trying to find the location that the friction force is acting on, or the geometric center of the distributed frictional load, right? So x is equal to, if you put it in a calculator, let's rearrange that, 20 times 981, factor x out, plus, is it plus 80 times x is equal to 80 cosine 30 times 0.2 minus 40 times 0.4. Then x is equal to this thing divided by this thing. Put in the calculator. Divided by so x is negative 9 10 to minus 3. In fact, it is nearly 0.09. Well, what do you get from this statement?
That
Is in the range. You see, this is, if this is the difference for x, what is this end? This is plus 0.4 or 40 centimeter, right? And what is this end? Negative 0.4 or negative 40 centimeter. Now my x that I get is what? Negative 9 millimeter. Almost a centimeter from left. Here. Negative 9 millimeter. Right? So what do you get? What do you understand from this numerical value? That the x is within the range. That means that the friction is valid and is not out of the range. If I get x is equal to 4 meters, like here, then what does it mean? If I get x is 4 meters, that means impossible. Which means that this thing is going to roll. Because the maximum possible that x can have is 0.4. And if it's greater than that, this thing will start to tip over, right? One side goes up, this thing will start to tip over if x is greater than that. So x must be within the range. The maximum x is 0.4.
But if that angle was different, then it is possible because of that, right? So if that angle was different, then that would, and that's an effect.
Let's say this height is 0.2, right?
Mm-hmm.
Let's say this was a long, like a very tall box, and this force was acting here, right?
Mm-hmm.
Then, in that case, it's possible that the x you
Okay.
get is more than 0.4 here. And then you just say it's going to tip over. It's not going to stay in equilibrium. It's not going to stay in equilibrium. This equation that I use, they're just enough to explain the phenomenon of equilibrium.
So if the x was inside that rectangle right there, it would not move over.
Yeah, in the range, But if x is outside that, that means the assumption we made for this geometric center is invalid. That means this equation are invalid. That means that this thing is a dynamic motion, it's not equilibrium. That means it's tipping over. We don't know what happens next, because we don't solve the equation for dynamics. We solve the equation for equilibrium. So according to this equations, the assumption is x must be within this negative 0.4 and positive 0.4. It should be somewhere between. If it's not within the range, these are invalid. Question?
How do you manipulate the moment equation to get that bottom equation out?
This one?
Yeah.
Well,
How do you go from there to the next equation? Not how did you get the moment equation, but how algebraically.
Yeah, in fact, you see this x, take all the coefficients of x and put them together. So one coefficient is 20 times 981, and one coefficient is 80 times sine 30. And this is sine 30. Sine 30. So these are coefficients of x, right? And then you take this to the right hand side, 80 times cosine 30 times 0.2, and then the other one, 0.4 times 80 sine 30, you come here to the right hand side with a negative sign. Because here is positive, you take it to negative. This is 80 sine 30 multiplied by 0.4, and since you take it to the right hand side, you take the negative value.
But you have 80 sine 30 on the left side too. So how do you have both?
Well, you take this value, what's the value of this one? Put it in the calculator. You take the value in the calculator, 981 plus 40. So this value is 236.2, and this value is equal to sine 30 0.2. That value is negative 2.14. So x is equal to negative 2.14 divided by 236.2. It's just rearrangement. I just rearrange this equation. Right?
Yeah.
So this thing is not going to tip over. It's going to stay in equilibrium. Why? Because the x is within the range. In fact, the x is very close to the middle. Okay? Now, let's go and solve this first two. So we already solved this equation, right? So let's solve these two. So from the first equation, f is equal to 80 cosine 30, which is equal to 69.3. And n from this equation, n is equal to 20 times 236.2. Right? So these are all unknowns I have. So I solve all unknowns. Now, in order to answer the question, does it move, does it slide to the right or stay at equilibrium? I asked the question, what's the maximum possible friction force? The maximum possible friction force is Fs, the static. You remember last time we had a graph of this, and say if you increase P P, the friction force is going to go up, and this is Fs, the maximum equilibrium friction force is setting. After that, if you increase friction force, if you increase P, this F is not going to go up. It's going to go down. And then this is the terminal value, the kinetic, K. Okay, it's slowly with constant velocity, right? So the maximum friction force is equal to mu S times N. This equation, we had this equation. So the maximum force that I get, F max, is equal to mu S. Mu S is 0.3 times the normal force. What's my normal force? The normal force is 236.2. Is equal to. So the maximum force 0.3 times 70.86. So this is the maximum friction force before the object is starting to move or slide. Now what's my actual friction force?
69.3.
So this actual friction force is smaller than maximum possible, the potential. So it's not going to slide. If that was greater than that, this equation would not be possible to hold on. The equation of equilibrium. So the conclusion is that this thing stays at rest. It's not going to slide and it's not going to tip over. Okay? Now let's solve another example. Initially 0, right? So this surface, there is a hinge here that we can increase theta. There is a mechanism that we can increase theta. So let's say this is originally 0. So this body, this box is on a flat surface, right? Then we can use this mechanism to increase the angle. And you can see that at some angle, this is going to start sliding down. The question is, what is that angle? Now, after it slows down, it's going to accelerate, right? You see that? Then we have to lower this angle in order to keep the constant sliding friction, constant sliding velocity. Then what's that angle such that constant sliding will happen with the constant velocity? And the third part, it says, find the maximum height of this block such that it won't tip over. This is a very practical problem in the industry. So, what should I do in order to solve this problem? Again, I have my class says, well, I don't write it. I just know what it is. I've written it so many times. So the system, what is it? The only choice of the system?
In the box.
The box, because this is just a constant mechanism. The one that moves is this, the one that we are interested in studying, right? So that's my system. And you know that if that angle is theta, this angle is what? Theta. Same theta. Right? So if that's my system, box, now I want to find surface force, body force. Pick a point and start moving. The first thing you have is the friction here. So what should I put here? A normal force, a friction force, and an unknown location shift from the center. Because we don't know this, like exactly like the previous example, right? So you would get F, the friction force is going this way, F, unknown, the normal force is this way, in, and with respect to center, let's say this box has a little bit of height. Let's emphasize on the height. Because there's a little bit of height in it. Right? So, the center of this object, let's say the center is right here. So this distance is x with respect to that center, okay? So the friction force is unknown value of F, but we know that it's opposite to the potential direction of movement, so that's the reason go up. And the normal force is always upward. And the location with respect to center is unknown. So we have three unknowns, 1, 2, 3, just because of this concept, right? Then you go around it and come back here. So that's the only surface force. What about body force? Do I have body force?
Mass times gravity.
Yeah. So mass times gravity, and assuming that this is uniform, mg comes here, and this angle is theta, right? So I chose my system, and I made my FED. Now I'm ready to write the equation. Okay, last example, the coordinate system was XY. This way. I can still use that coordinate system, but the equations become a little bit longer. So the trick here is, I can, as I said before, you can move it anywhere, or you can rotate it. I will rotate this theta degree down, and I align it with this system. So that would be my X, and that would be my Y. And just I rotated theta degree down, right? So it's aligned with my object. Now I'm ready to write my system of equations. The summation of force in the X direction, 0. Summation of force in Y direction, 0. Here X and Y is this. X and Y. Don't get confused with this. Right? In this direction, that direction. And summation of moment, 0. Right? So the first equation would give me, let's start with F. What should I write?
Negative F.
Huh?
Negative F.
Negative F. Then go to this guy, 0. Right? This guy.
0.
It's not. You see, this is X. This has a component in the X. So what's the component of this guy in the X direction?
Yeah.
Yeah. So plus mg sine theta. What else? That's all. 0. Right? The second equation in the y direction. This one, 0. The second one, positive n. Right? Negative mg cosine theta is equal to 0. And the last one, summation of moment around any point is 0. What point should I choose for moment?
Or N and F are intersecting. Yeah.
This one, right? Because I get rid of these two unknowns immediately. So that, let's call it A. So summation of moment, what? Point A. Sub A, 0. So I can immediately see that 0, 0. So this guy will have a mg sine theta, mg cosine theta. So this is mg cosine theta. Where should I move it?
Down.
Down here. So the moment is equal to mg cosine theta times
X.
yeah, cosine theta times x. Positive or negative?
Positive.
Positive, thank you. Now the other component, mg sine theta, where should I move it? This way, right? So mg sine theta times
Half the height, h over 2.
h over 2, positive or negative?
Negative.
Negative. Sine theta h Really? Because this is H. See that? From here to here is H over 2, and from here to here, H over 2. So mg sine theta times H over 2 negative is equal to 0. So these are my equations, right? So, at the first, we want to solve the first one. Find theta such that this thing starts to slide down. So at that point, we have this equation. The friction force is a static friction force, the maximum, which is mu s times n. So at that particular angle, this equation is valid. So all I need to do to find my friction force and divide it by mu s to get my normal force. Then I get a relation between theta. So let's solve it. Let's solve this. So my friction force is always mg sine theta. And my normal force is equal to mg cosine theta. So this is always valid. And the x is equal to tangent theta times h over 2. Right? Take this to the right, mg cancel out. Sine over cosine tangent times h over 2. So these are the solution for the system. But in order to answer this, I also need to apply the equation that is valid at this particular point. The maximum theta is the point that the friction force reaches to. You see, this doesn't have a stop because it can be dynamic, friction, static, everything. It reaches to Fs. So at that point, we have Fs mu s times m, right? So just let's plot F and m in that equation in order to get theta move. So Fs is what? Fs at that point is mg sine theta. But theta is a particular theta that generates the movement. So this theta move, right? We're trying to find this. Is equal to mu s times n. At that point, n is equal to mg times cosine theta move. Theta is the particular theta, is the theta of movement, the angle of movement, right? So all I did, I said this equation valid at that point, I plug f and n into the equation, and then can I solve for theta move? Yeah. Or not? Yes. Look, mg cancel out, so tangent theta move, right? Sine over cosine theta is mu s. So theta move is equal to arc tangent mu s. Now, if I give you a typical value, if I say, let's say mu s is 0.7 and mu k is 0.3. Then what's the angle that this object is about to move? What's the theta move? Theta move is arc tangent mu s. Mu s is 0.7. So if you put in calculator, arc tangent is 35 degrees. So what does it mean? That means that if this angle is 0, there is no movement. If it's 1 degree, no movement. 2, no movement. Then you go up to 30 degrees. Is it going to move? No. You have to go exactly 35. And then if you add a little bit more, it's going to slide down with acceleration. And then you have to lower the angle. in order to keep the constant velocity. Otherwise, it's going to accelerate. If you keep just 36 dB, a little bit more than that, it's going to accelerate. If you want to keep the constant velocity such that equilibrium equation is valid, you have to lower that angle. Now, what is the angle that goes with constant velocity, which is a small angle?
UK.
The only difference, this equation is still the same. FBD the same, equation the same, solve the same. The only difference is instead of this equation, when it's moving with constant velocity, you have Fk is equal to mu k times m. That means in this relation, mu s is replaced with mu k, right? So theta, in that case, theta would be arctangent mu k. What's my mu k? 0.3. So arctangent 0.3. Arctangent 0.3 is 17 degrees. That means that you can't keep it like 36 degrees. You have to lower the angle. So initially it starts moving the acceleration, and then you lower the angle and it goes with constant velocity. Slide down with constant velocity. Now, if I say this length is 20 centimeters, let me give you some numbers. Let's say the mass is, let's say we have an object, right? The mass is 100 kilograms, right? And the length, the base length, displacement is 50 centimeters, right? 50, so it's this much, right? It's this much. And it's like a little bit heavier than me. So the question is, what is the maximum possible height before you start to tip over? Now you have some intuition, right? Let's see if you can get it. So then I'll use this equation, right? The maximum possible h that it will start to tip over happens when x becomes
26.
here. The tips, right? Become 25 centimeters.
If it's exactly 25, does it still tip?
No, this is about to tip. That's the thing. In fact, it's like you said, 25 plus something, like 26. That's correct. But because we are considering the onset of movement, we just say 25. But in fact, in 25, we don't know if it's gonna move or stay. It's kind of like unsure, right? So let's put 25 here and solve for h. So h is equal to 2 times x divided by tangent theta, right? So 2 times 25 10 to the minus 2, which is like this, half of this. This is 0.5 meter, then half is 0.25, right? 2 times that divided by tangent. Now say tangent theta, which theta? Then you ask, well, at what situation you don't want to tip over? When it's at rest or moving with constant velocity, then just use that theta. Let's say the rest. Let's say the rest. The rest, the theta max was, what's the maximum angle when it's at rest? 35. So I put in calculator. 2 is 0.714 meter or 71 centimeters, which means this much. This much. So if your box is a little bit harder than this one, start to tip over.
So if we go back to the original problem,
Yeah.
the mass of that box has nothing to do with the angle at which that box starts to
No,
move?
no.
Why wouldn't it? Because the heavier the box,
No, because you change the angle. Because you change the angle. So that angle is only governed by the friction. Let's consider like this. Let's say there is no friction, like in an ideal world. What happens? I'm staying, the box is staying here, the angle, let's say it's originally flat, 0. What happens? The object is at rest. Now, if I increase the angle like 0.0000001 degree, it's just stupid. But in that case, this should start to move and accelerate, such that it reaches infinite velocity.
Yeah.
That's completely non-physical. But in the actual physics, it still remains on the surface because there is friction.
Friction,
And
yeah.
you increase the angle, it still remains on the friction, on the surface because there is friction. Such that you reach to 35 and start moving. And interestingly, you may say, well, if the weight is heavier, you may slow it sooner, right?
Mhm.
But that's not true because that's probably wrong intuition. Because the equation that they tell us, that's the reason I say you have to do 5-step system, FBD, writing equation, solve. Because if you don't go to the right procedure, to the correct steps, you easily get confused. So, and that value is also making sense. So, if this base is, what was the value of base? 40 centimeter. What did I use for the base? Yeah, 50. If this is 50, right? If this is 50, the solution tells us that this should be 70. 71?
71.
71, right? You can easily say, well, last step was verification, right? You can easily say, well, if this is 50, this is 70, a little taller. But if you get like 600 instead of 70, if you do a wrong calculation, you use 600, then you say, well, in actual physics, if I have a box like that, it will definitely tip over. So I'm not getting the right value. But here, we have some kind of proportion. And obviously, if this is less than 70, like if this is again 50, like a pure box, it's more stable. And if you are smaller than 50, it's like this. It's even more stable. Like you see some cars, they're more stable because the height is smaller than the base, right? So it all comes from the simple analysis. As an engineer, you should be able to apply the mathematics. And what was the mathematics? Sum of the moments. That's the reason we say finding the moments is very important. So we didn't do cross product. You see, I could, but I did not. I used my fast method of moving components. But the end result is you can tell as an engineer, you can give them the values 70, 50. As a designer, you can come up with some numbers, actual numbers. So these are precious, these mathematical tools, because they have applications. You see that? All right, so let's close it at this point. Next class, we're going to talk about the truss analysis, which is very simpler than that. It's very systematic procedure. And I'm going to post homework today, hopefully not tonight. And the deadline is at least 1 week, at least.